There we
Yeah, I
go.
don't expect to take the full hour and a half, so it won't take that much time. We got time to goof around with technical problems. I want to get Andrew back if we can.
Sean, I got an email from Wolf asking for him to use my fluorescent scope, and I don't understand why, because I don't have a fluorescent scope. So I just referred him to you.
Is Wolf actually on campus? I haven't seen him.
No, I just got an email from.
Yeah, I mean, that goes over to Monica. So you can unmute Monica here.
Okay.
Monica, you there?
Yes.
Did you hear what Dr. Pierce was saying about getting a request from Wolf about using a scope?
Yeah. Is this a second email?
Yeah.
From the previous one?
Well, he just he emailed me. Yeah, this is a second email, and he emailed me
Okay.
saying that he wanted to, he wanted to use my scope and wanted to know if I could have one of my staff train Andrew. And I thought that was kind of unusual because A, I don't have a scope, and B, none of my staff are coming in. So I referred him to you, Monica, and you, Sean, so that expect a call from him. But I also told him that, all of our routine use of the AIM facility is on hold until we open up again. Right, you're technically shut down, right?
Yeah, you guys are shut down, right?
Yes. Yes, until April. That's what Dr. Hughes recommended us to do. So just following orders.
Yeah, so you're shut down through the end of April, but then starting the 1st of May, you'll be back for regular business, right?
She didn't exactly say that. She just says we'll just play kind of by ear. They're just going by what, everybody, the news and the CDC, everything like that. So she didn't say that we will be open. She just said we will keep in contact. So as of what she said, I'm assuming until April, but I really don't know afterwards.
Well, the state is technically on a stay-at-home order through the 15th of May.
Right.
And I
think that's what I heard on my end, but I haven't received an email from her. So I'm not sure if Dr. Wilson received an email. He could let us know, but
which one?
I'm not sure. I think he got disconnected or something.
He was having problems with his bandwidth, so now it's up to us. Oh my goodness. Are you a co-host on this meeting, Monica? Because Andrew's not back yet.
Oh, he's not back?
I haven't seen him.
I don't. Let's see.
Hey, Kayla,
Andrew,
can one of you guys text Andrew and see if he's okay?
Well, I already did. I haven't received a response.
Oh my goodness.
I got disconnected. No, he's not back yet.
He's not back yet. Okay. Well, I mean,
think he was trying to connect via phone because that's what, he had the phone icon there.
Yeah, his computer's been, when did it break? Tuesday, guys? Do you remember?
Yeah.
Tuesday. I think it was Tuesday night. We were trying to do some computational simulations in Denise's class, and I think we blew up his computer.
Well, in this particular environment, having a good computer is essential for connecting to the world.
Yep. I don't know. I'm using a 5-year-old ThinkPad that I've got Linux on. It's working fine.
It doesn't matter how old it is. It matters how well it works.
Yeah. Well, ThinkPads running Linux are like Ferraris. Speedy.
I am looking forward to being able to use
Dr. Wilson's been sucked into the Matrix.
He sounds like a robot.
We cannot understand you, Sean. What's happening? Poor guy. He's been digitized. What are we gonna do?
We can start without Sean, but we can't really start without.
I'd like to have Andrew on, particularly if he's going to need to learn something about fluorescence. I don't talk a lot about fluorescence today, but it's something that I can elaborate on if that's something that he wants to know.
So I'm not really sure what has been covered, what the topics are. I mean, I presume that there's already been lectures about the fundamentals of fluorescent microscopy and image capture and construction and all of that.
Yeah, this is a great time for Kaylin Folu to get us up to date. I have no idea either.
Chris,
Yeah, we went over a little bit of
why don't you go ahead
cell counting
and
and
get
image J.
started?
Okay, I can get started. I think that's what Sean's saying. Okay, well, I can Andrew's got the slides, and I can always run over it again with him sometime. So what I'm going to talk about
Yeah, so
today.
long
What was that, Sean? This is always the awkward thing. You guys should get on YouTube and look for, there's a video from the New Zealand Police Department, and it goes over all these different Zoom related problems. It's hysterical. It's the funniest thing. I'll try and find the link and send it to you guys. Okay, what I'm talking about today is unbiased or design-based stereology. So usually we just say unbiased, but in fact it really is a design-based method. I'll talk a little bit about the history of unbiased stereology and sort of why we are where we are right now when it comes to trying to count objects that are in three-dimensional pieces of tissue. You guys know how to get hold of me. Don't send email to that C. Wilson guy. Send it to CG Wilson. And if you can annotate the slides, it's helpful. So stereology came into our lexicon back in 1961 after a big meeting. It was the International Society for Stereology. They met in 61 and 62. Hans Elias is probably one of the most eminent quantitative biologists that came out of the Copenhagen microscopy program. And he was, at the time, he was one of the editors of the International Society for Stereology, or one of the leaders of the International Society for Stereology, and there's a journal that's associated with the society. I think it's called the Journal of Quantitative Biology or Quantitative Microscopy. Anyway, they wrote this paper in 1962 where he coined this term stereology to refer to how you quantify objects in 3D space. So that's really the whole definition of stereology. And that includes, can you guys see my cursor?
Yep.
Yes.
Okay, good. If I need to, I can turn on trails because I'm on one of my laptops. But anyway, so this includes quantifying 3D objects in biological samples and biomedical sciences. But really, the concept of stereology and trying to understand how to identify objects in stratified soil comes from geology and material sciences. So really trying to count objects that are embedded in a 3D matrix comes from those disciplines. And of course, as you can well imagine, that includes things like civil engineering and understanding how to define, aggregates in concrete and stuff like that. So the early literature on quantitative stereology and unbiased stereology really comes from this idea of trying to figure out what things look like embedded in amber, embedded in geologic layers in anthropology or geology. So that's really where it comes from. So literally, it's been 60 years since this whole concept came into being. And within the last 20 years, we've moved towards these more unbiased or design-based tools because we now have computational power that can help us do these things in an unbiased way. And stop me if you have questions. I talk fast. You guys know that. Why the 1960s? So when you think about the development of technology, the mathematical foundation that we needed, and in this case, the International Society for Stereology issued this authoritarian statement that said, if you want to publish papers that are using some kind of counting of 3D objects, you have to use a stereological method that's validated and verifiable. So really, technology, meaning that the electron microscopy world had blown up by then, so electron microscopy was available. Good bright field imaging and optics were available and easy to use, and computer technology was just starting out. And it wasn't really something that was integrated with optical workflow and trying to analyze images, but it was the beginning of the computer age too. That started in the 40s, but it wasn't until the early 60s that mini computers, not microcomputers, but mini computers and mainframe computers could be applied to these sorts of problems. The mathematical foundation really came about in the middle part of the 20th century, where we had people who were interested in understanding how to interpret microscopic images, and particularly dealing with something called the corpuscle problem, which we'll talk about a little bit today. So the mathematics was really well developed by the time the 60s came along, because people were trying to figure out, how do you deal with this concept of bias and making sure that you're only counting one of an object when you need to count one of an object, or you're getting the full 3D structure from two-dimensional projections. So that's why the mathematics became important and was developed in the mid part of the 20th century through the early 60s. Okay, what's stereology good for? There are only 4 parameters that we can quantify directly, what I call first order parameters, or what the field calls first order parameters. Those are volume, area, length, and number. When you think about density, and I'll talk a little bit about density, density is a derived value. You're talking about the number over a given volume or the number over an area. And there are inherent problems with bias and uncertainty in acquiring each of these particular parameters, volume, area, length, and number. But they are the first order parameters that we can actually count in an unbiased and reliable manner.
Hey, Chris, all I'm seeing is your first cover slide. I see the rest of the slides and the margin on the left. I would assume that you're up to slide number 3.
Okay.
There we go.
Well,
There
let me fix that. Let me make sure I'm sharing the right screen. What I'll do is share my desktop. I'm sorry. Has that been the case for everyone?
Yeah, that was
Yeah.
intentional.
Well,
Sorry.
you guys got to stop me, man.
I did.
Okay, thank you. Could have, you students are just, you got to say, okay, we're going to stop this guy. Okay, can everybody see the slideshow now?
There you go.
All right. Sorry about
Yes.
that. That's my bad. My bad.
That's all right.
Okay.
We know that you don't understand this very well and you're new to computers, so we'll give you extra patience.
Well, Zoom is a little tricky, I have to say. So the 4 parameters that we can quantify is were volume, area, length, and number. For the rest of the talk today, I want you to think about those things, because we're going to talk about dimensionality in relation to those particular parameters and how you can use those parameters to figure out what's happening with a 3D object. So the dimensionality becomes important when you're talking about how you quantify these particular parameters and what probes you use in order to do that quantification.
Chris, I have a question, a really fundamental question for me is that a lot of times we've done cell counting and relative area in 2D slices, and we've received some really wild criticisms that you can't, this data is uninterpretable, it's totally ambiguous, and the only way that we'll accept this is if you do total 3D stereology. And to me, it seems a little crazy because a lot of, particularly in the work that we do, which has based a lot on coronal slices and measuring TTC areas and things like that, that it's all based on analysis of 2-dimensional slices. Is there a set of assumptions or qualifications that you can make to say, well, yes, we can get this information, but we know it's subject to this limitations? Or do we really have to start, insisting that we try to develop 3-dimensional models of our infarct volume before we can publish the response to an ischemic stroke?
Well, I'm glad you brought that up. So the people who are criticizing you are absolutely right in what they're doing. Now, the exception is that when you're talking about 2D objects that you can count, there has to be a sparse population of those objects, and you have to be able to accurately, reliably, and regularly count everything that is in your volume or area of interest. If you can't do that, then everything you're doing is biased. And I'm going to talk about one of my favorite saws, and the students have already heard this in our Monday seminars, is people who try and draw a line around an infarct and use that as a method of quantification from a 2D image. So it's an invalid method stereologically, and they're exactly right. You need to use a 3D unbiased or design-based stereological method to quantify infarct. And I'll talk about that and why that's a problem. I'll give you some of the background for that.
Okay.
Okay, so platonic solids versus biology. The big problem that we have is if you look at the material science world and the geology world, often they're dealing with things that look like the Greek platonic solids. They're very regular, spheroidal, or cuboidal. So if you slice through these objects that are 3-dimensional in 2 dimensions, you can actually reproduce the 3D structure of those kinds of tetrahedrons and icosahedrons, these platonic solids, readily and reliably. So these things all come from the Euclidean geometry world. If you don't remember Euclidean geometry, don't worry about that so much. But when you look at these shapes, tetrahedrons, octahedrons, cubes, dodecahedrons, icosahedrons, and then you compare those to naturally occurring objects like neurons and microglia and astrocytes, these don't look anything like the platonic solids. Therefore, the idea that you can take a 3D object, slice it in regular 2D segments, and then come up with something that looks like a naturally occurring object in biology is somewhat fallacious. And you have to be very careful about the constraints that you use to try and represent biological objects that have been quantified in 2D sections in the 3D volumetric world. So keep that in mind, that the idea of stereological or stereometric measures comes from these platonic solids or things that are relatively simple in shape. And that is not the case for us. So really what we're talking about, the difference between Euclidean geometry and stochastic geometry. What is a stochastic thing, oh students? What is a stochastic thing?
Random.
That's exactly it. So it's random. So the idea here is we use random sampling or stochastic methods as a way to guarantee that we're actually quantifying an appropriate number of biological objects. And I'll talk a little bit more about that momentarily too. Okay, so this is the fundamental problem. We're dealing with something that we're not trying to quantify things that are regular. We're trying to quantify things that are irregular and very complex. And complexity and resolution are deeply interrelated. So we'll talk about that too. All right. Let me just give you an idea. You know, 1961, 1962 is when microscopists started talking about unbiased stereology. Excuse me. And from that point on, there was this drive to start developing automated methods to do stereology or methods that were computer assisted, and to come up with ways to quantify 2D or 3D biological objects using 2D sections that then can be translated into 3D objects. So all of the papers, and this is only up through 2010, I should probably update this, but there has been nothing but an increase in the number of papers that are published using stereology, with a subset of those using unbiased or design-based stereological methods. Okay, and you can see that the real peak here, I want you to pay attention to this inflection point. If you look at the inflection point here, about 1990 to 99 approximately, what do you think changed? Why in the world would that change?
Technology.
Hmm?
I said technology.
Yes, what aspect of technology? Automatic transmissions? Flat screen TVs? Tell me what aspect of technology, Folu.
Huh.
Hmm?
I'm not sure exactly.
What year were you born again?
95?
Oh,
I know,
yes.
I'm digital.
The technology of Folu came into being. Excellent. So now we have Folu technology. You don't remember an era before microcomputers that were powerful enough to really handle 2D and 3D streaming images, do you?
You know, briefly.
Yeah, I think I got my first cell phone in 1997 anyway. So what happened in the latter part of the 90s is microcomputers really became powerful. So this is when we started to move from the 8-bit world in the early 80s to the 16-bit world in the late 80s, and then the 32-bit world. And the 32-bit world of processors, the early Pentium processors from Intel and the Motorola PowerPC processors that were running Macs at the time, were really capable of doing things like looking at images and acquiring images very rapidly. In the days before that, we had to use very expensive coprocessors to acquire digital images or analog images that were then converted into a digital stream that we could actually quantify within a computer. So technology did change, but it was mostly computers and the ability to deal with 3D volumetric images in a 2D space and reconstruct that information. So it's about matrix math and being able to do matrix math fast and handle full 24-bit color images. All right.
Wasn't there a lot of advances? Weren't there a lot of advances in imaging as well? Because now you have the rise of CT scanning, you have the rise of construction, now you have the rise of the very beginnings of confocal microscopy. You have all of that. So there was a demand. So you had the computer power starting to develop, but you also had the ability to generate huge amounts of image. So that when we went from an 8-bit image, microscopy image, to a 12-bit image, I remember, wow, it was like such a huge improvement. And big number, a 16-bit image. Wow, that was like really superb. And a lot of us are still looking at 16-bit images.
Oh yeah, absolutely. And well, most data acquisition, even for electrophysiology or imaging, is really 16-bit. And we fake it and put another 8-bit transparency layer on top of that to make it 24-bit. But it's not true 32-bit color. You're absolutely right. So absolutely correct, Dr. Pierce. So one of the things that came about at that time, how many of you have heard of a thing called a CCD? Do you know what a CCD is?
I do.
It's not a certificate of deposit. It's not financial at all. Kayla, do you know what a CCD is?
No.
Do you know what a CMOS is? A CMOS chip?
No.
Okay. So your phone has a lovely camera in it. And if you have a digital camera, then it has a sensor in it too. Back in the late 90s or early 90s, late 80s, charge coupled devices were one of the first imaging technologies we had that were truly digital, from the source of light gathering, detecting the photons, all the way through to the data stream out. So way back when I was a graduate, I'll give you one of these old gray-haired man stories. Way back when I was a graduate student, we had to use analog cameras, just like they use for TT or for television production in the 60s. So basically, these are cathode ray tube-like devices that detect photons, translate that into an analog stream, not a digital stream, back in the 60s and 70s, and then they carry that through to a television that was a cathode ray device that then would use magnets to actually alter the stream of electrons from 3 different guns, if you're fortunate enough to have a color TV, and then display an image. So it's not inherently digital. So it wasn't until this period in the late 80s and early 90s that digital sensors started to become more prevalent. And as Dr. Pierce mentioned, that meant that we could collect images very readily from the outside world, the analog world around us, looking at a microscope through glass optics, and convert that into a digital data stream that we could then manipulate with the computer. So we moved from the analog imaging world into the digital imaging world, sort of at that border in the late 80s and early 90s. And ever since then, you know, we didn't have phones with cameras until, I don't know, probably you guys were in short pants, right? Folu, you're probably 12 when you got your first cell phone, like most people in America.
Yeah, it was I don't even know what, a slide phone, some kind of thing.
Oh, cool. Yeah.
Mhm.
Nokia slide phone. You were truly matrixed up. So, but did that phone have a camera or no?
No, I don't think so.
Okay. So there was, you know, these originally charge coupled devices were the first digital imaging technology, and we use those in our fancy microscope cameras that we use on cameras in the AIM or cameras in our labs when we're doing any kind of fluorescence work or bright field work. So now CMOS sensors have largely replaced CCDs, except in very high-end functions like NASA telescopes still use charge coupled devices because they're very low noise and they're very efficient at cold temperatures like in space. But CMOS devices, basically you're printing the sensor right on the chip. So you're using normal chip layout technology that we use for developing microprocessors to actually make an optical sensor. So a CMOS sensor is basically what a CCD used to be, and that's replaced all the digital imaging. And that's the stuff that's in all our cameras and in most of our microscope cameras now too. Okay, technology history lecture over. Thank you for asking the question though, Dr. Pierce. All right. So unbiased stereology depends on this, how do we determine what's accurate and precise? And you guys have heard about this before, I'm sure, in some of your lectures. So on the left here is this sort of classical image of a target, whether it's for gunfire, which we don't talk about here in Loma Linda. We don't do guns in Loma Linda, right? Or arrows or BBs or slings, whatever you want to use. What was that? Darts. Yeah, darts is a good one. So if you're looking at darts, if you're English and you want to look at darts, this is an important image to understand. On the left is a column that deals with unbiased hits on that target. On the right, we have biased hits on that target. Horizontally, we have high precision, so the hits are relatively localized tightly together. And on the bottom horizontal plane, we have low precision, and you can see that we have a wide cloud. So normally what happens is there's a certain amount of bias in biological systems that we don't know about. There is noise in the system. So when you have a bias system, you're trying to be precise in your measurement. You're trying to use high precision in your measurement, but there's bias that takes you off the center of the target, and you don't necessarily know what that is in the biological world. If you have a gun, it's the sights. So you need to change your sights so that you then have high precision that's unbiased and is very localized around the target, your goal that you're trying to shoot at. If we look at the low precision column, if you're biased, you can see that if you look at the geometric mean of this cloud, if you do a k-means clustering measurement or the geometric mean of this cloud, you can see that it is very far off the center of that target. So it's way over here. If you're using an unbiased method to do that, you're going to have spread all over your target. You're still sort of on the target, but you don't have that bias shifting you off of the center. So the idea here is an unbiased method will give you an accurate representation of the data that you're striving for. And high precision means you have low variation. So the two things that we always have to deal with in the biology world is inherent bias that we don't understand and can't fix. And precision, low variation, is something that we can do relatively easily in many systems. But in biology, there's biological variation, so we have relatively high variation. So our goal is to get unbiased high precision, but we often end up with biased low precision in our experiments. So the unbiased stereological method is meant to give us accuracy with a desired level of precision. So we have high accuracy with as little bias as possible. So we try and eliminate as much bias as we can by using good methods, good sampling methods to try and reduce that bias. Okay, I hope that makes sense, and I know you guys have seen these before. So using an unbiased method with sufficient precision to confirm group differences at p less than 0.5 is what, or 0.05, is what we typically try and do biologically. And that would give us this, we have a certain amount of precision variability, high variability in a biological system, but we're relatively precise and unbiased in our method of sampling. All right, so that's the central problem. If you have bias that you can't control and low precision in your method, then you're going to have inaccurate results that deviate from truth. Notice I'm using quotes when I talk about truth here. Okay, neurostereology, that's funny. There should be something there, don't worry about it. Let's talk about these first order parameters that we talked about a little bit earlier. Here's a table that has parameter on the left with the dimension of that parameter in parentheses next to it. And then the structure that we're trying to figure out or quantify. The probe that we can use with its dimensions that allows us to assess that particular parameter. And then the total sum of the dimensions. Now, for an unbiased design, it means that the parameter with its dimensions and the probe with its dimensions must equal or exceed 3. Okay? Does that make sense? Because what we're talking about is trying to quantify a 3D object in space. So in order to quantify that 3D object in space, we have to have all 3 dimensions at the end result in order to accurately and precisely quantify what that 3D object looks like. Okay? So if we're interested in volume, we know that's a 3D parameter. We know the structure that we will get when we try and assess volume is volume if we have all 3D parameters. We're not talking about time here. That's a whole nother dimension. So we can use a point to assess volume. We use Cavalieri points. A point is dimensionless. It has a dimension of 0 because it's a point. From your geometry, I hope you remember that. So when you're looking at volume and you use points to assess volume, you obtain those 3 dimensions by using those points. If we're interested in area, area is a 2D concept or parameter, x and y. We want to get a surface if we're looking at area, a plane. And the way that we assess that is using a line. So we take 2 dimensions, we use a line to assess the surface, the area that we're interested in, and that gives us 3 dimensions finally. For length, it's 1-dimensional. We can look at curves with length. If we're looking at length, we're trying to measure curves in the biological world. We don't see straight lines so much in the biological world. We can use a plane and intersect that line with the plane, and that gives us the additional dimension that we need. The reason I bring these things up is because the computer allows us to do these things very readily when we're trying to assess these things. Now, if we just want to count something, remember we talked about a point or a number being dimensionless. We want cardinality. We want some number at the end. We use a dissector, and I'll talk more about dissectors in a moment because dissectors give us a 3D space that we can use to go across objects that we wish to count in space, and that will give us the 3 dimensions that we need in order to quantify the number of objects that we see. So the probes that we use are things that we can generate in the computer. You can do all of these things by hand, believe it or not. It's very difficult to get a 3D dissector structured that you can use to count. So the computer is really the only way we can use a 3D dissector. But you can use points, lines, and planes to quantify images with a pen and paper, or a transparency that you want to lie on top of an image that you're trying to quantify. So the idea in the end is we have to have all 3 dimensions in order to get these things to a full unbiased resolution. So that's accurate first order stereology. And notice I've not talked about density here at all. Okay.
A quick question about, could you give a little bit more detail about cardinality?
Sure. So cardinality is just, you remember the data analytics class when we talked about category data and numbers?
Mm-hmm.
So cardinality is dimensionless in the sense that we're taking a number that has a 0 dimension. It just represents a concept in our minds. It doesn't have necessarily a physical representation because we're counting an object. We're counting something that has volume, area, and length maybe, but we're only iterating a counter of that particular object. So that's what I mean by 0 dimension for the number. And cardinality is the actual final number that we're trying to find, the number of objects that we're counting.
Got it.
And then the dissector is what we use to do that. And I'll give you an example. This is unfortunate. You know, I was trying to figure out a way to put a bunch of animations in here and do this online. And I've got some videos that I want you guys to look at that you can look at on your own time. But what we'd originally planned to do, the other Dr. Wilson and I, was have you guys in the lab and we can actually show you the software and give you some examples where we're using the software to do each of these things within the lab. So until we're back in the AIM, we can't do that. Okay, let me just make a quick point about the Cavalieri principle. Cavalieri was an Italian microscopist, and he was really interested in understanding how to assess volume. And we'll talk about the corpuscle problem in a moment, but one of the things that you can do very easily to assess volume is use these Cavalieri crosses or points. So you can use points and overlay those points on an object and then figure out the total volume of that particular object of interest that you're looking at, the region of interest that you're looking at here, because you know the volume of the cross. You know the area of the cross in a two-dimensional plane. And as you serially section through that 3D object using these planes, you know the distance between the planes that you sectioned, and you know the area of the cross. So you can actually get volume very accurately using Cavalieri principle and using Cavalieri point counting, okay? So determining the volume becomes a matter of your point resolution. How many points you need to count for a given object, and that depends on the size of the object and the region that you're interested in counting the number of objects in or counting the volume in. So this brings us to this idea of the coastline paradox. How many of you have heard of the coastline paradox before? Ah, Dr. Pierce has. He's a wise man who's been around the block a bit. How about the rest of you? Kayla, have you? No? Folu?
Nope.
Did Andrew ever get back or no?
No, don't see him.
Okay. So the
No, I sent him an email, but I don't have his cell number.
Okay.
Yeah, he
Well,
said he won't be able to join right now.
okay. Well, I'll try and make up the time with him. I can have this discussion with him on Zoom another time. So the coastline paradox has been known about for a long time. It's counterintuitive because typically you think that, okay, something like England should be a coastline circumference that we can quantify relatively easy, right? That's what surveyors do. You send a surveyor out, they've got a tripod with an optical bit on it. They got another guy with a stick, and he goes and he measures the length out, and you can measure the rate of change of height, the total altitude of the point that you're trying to assess. That means that you could send out a bunch of surveyors and they could just walk around England, and you should be able to get the circumference of England in this case, the coastline, right? However, it turns out that's not true because of fractal-like properties that we see in natural systems. So what's a fractal?
Favorite object, things that just repeat, like you zoom into it or at any point it's supposed to be like symmetrical.
Yeah, that's a good practical definition of what a fractal is. You're absolutely right. So the idea here is fractal-like objects, and you can talk about the coastline, you can talk about trees, you can talk about the dendritic tree on any kind of neuron or microglium or astrocyte. They actually have a fractal dimension, which means that we can't really easily assess their length. It depends on the resolution that we're measuring the object at, what length we actually can acquire and quantify. So if you're using a relatively low dimensional metric to try and measure something, and I'll show you that in the next slide, then you're going to get an inaccurate measure of the length of that particular thing, in this case, the coast of England. But based on the resolution that you use, maybe that's good enough. And why would that not be good enough? That's sort of the question that underlies the philosophical discourse on fractal dimension. So this sort of thing was first described phenomenologically and mathematically by Louis Fry Richardson and later Benoit Mandelbrot. So anybody know about the Mandelbrot set of numeric families? It's a set of functions.
Mm-hmm.
Okay. So anyway, I could show you a screensaver that makes Mandelbrot-like functions with the idea that as you zoom in closer to an object, exactly what Folu said. Here's a Koch snowflake. So here we have a triangle. Let's say we zoom in on that, and the closer we get to these edges, we start to see more and more resolution. And the whole idea of fractals is that they have repeating structure. So if you have a high fractal dimension, it means that it has high level of reproducibility or repeatability as you zoom in on it. So this is taken at one magnification, if you will, but you can see that if you zoom in, you're going to have increasing numbers of these triangles at the edges that you start to perceive depending on the limit of the resolution of the object you're viewing that thing with. So in mathematics, fractal dimension is a ratio providing a statistical index of complexity, comparing how detail in a pattern, a fractal pattern, changes with the scale at which it is measured. So the pattern, the complexity of the thing that you're looking at will change when you change the scale of resolution that you're looking at that particular object. So this is a relatively simple example. It's a non-trivial example if you try and do the math, but a Koch snowflake is this thing on the right. It has a topological dimension of 1, but the length of the curve between any 2 points on the snowflake is infinite. Does that make sense?
Mm-hmm.
So if we take a measurement here and here, and we zoom in, what happens is we start to see that it has embedded structure that we didn't see at that lower resolution. And as we zoom in even more, we see that in fact, the closer we get to trying to define the length of that particular segment, it becomes infinite because it has fractal order like that. Okay, no small piece of this thing is line-like. Instead, you know, at the resolution we look at, it's like, oh, that looks like a straight line. But in fact, as we zoom in, we see an infinite number of segments joined at different angles. So it becomes very complex the closer we get to trying to determine the edges. The fractal dimension of a curve can be explained intuitively, thinking of a fractal line as an object too detailed to be one-dimensional, but too simple to be two-dimensional. So try and wrap your mind around that. I want you guys to think about this. This is the sort of thing that should keep you awake at night like it does me.
But in reality, there's a certain amount of pragmatism here because you can basically define this by how quickly the distance between the 2 points rises as you increase the resolution, as you increase the scale.
Yeah, so, absolutely. Yeah, you can use a derivative kind of
right.
assessment of the edge effect too.
Right.
You're absolutely right.
In a lot of statistics, one of the things that's really handy is you say, well, I could go on forever and make it infinite. We can't make any measurement. No, it's not true, because you can set a certain scale and say, at this scale, I can compare these two things. And if I can see a significant difference between them, then I report that. But you always also have to report the scale at which you're making your measurement.
Absolutely. And that is the caveat for so much infarct measurement that I've seen over the last 30 years of my career. You have to say, this is the resolution that I'm using, and this is the pragmatic ability of me to quantify the data that I have, even though that's not the best philosophically or theoretically. Okay, so here's an example. This is just a GIF of exactly that sort of thing. This is a Koch line in this case. So it's one of the segments that makes up the Koch snowflake. And you can see that as you try, you know, it starts out easy, and as you try and measure, it's like, oh my goodness, it's getting complex. Now it's getting much longer. So the concept of length has no meaning when you're talking about something that has fractal dimension. That's the problem. Okay, so let's take this back to the idea of the coastline paradox. Here's Great Britain. So here we're not just talking about England, we're talking about Wales, we're talking about Cornwall, we're talking about Scotland, Isle of Skye, all that stuff, whatever. So now the resolution that we're using determines the length that we're going to be able to quantify and measure here. If we only use, yeah, go ahead, Bill.
That's what I'm going to say. Yes, this is the really pragmatic point, and you have to, the real secret here is knowing where to draw the line.
Exactly. Or if you need to draw a line. In fact, you don't need to draw a line if you use a different method. Okay, so if we use 9 segments to try and quantify the coastline of England, you can see that that's very rough resolution, and we're not going to do even close to anything like a practical, accurate job of assessing the coastline length. If we go to 19 segments, it starts to look more like the outline of Great Britain. If we go to 48, you can see, yeah, okay, it looks even better. And then 97, we have an even more what we would call accurate and precise measurement of the coastline length, okay? But you can see that it changes with the raw length of the segment that we're using and the number of segments that we actually try and use to measure. How does this work in the real world? So here's an example, exactly what Dr. Pierce was talking about before. Here's the website for these images if you're interested in looking at it there. I'm not going to name the investigator. Here are some hearts, and they're using TTZ staining. And what you see is the healthy tissue is relatively red. The damaged tissue is white, if I'm getting that right. Is that right, Bill?
Yep.
Okay. So how do we assess the size of the infarct, the damage to this heart? What people have done for the last 40 years is they draw a line around it with image J, and then they use the tools that are in image J to add up all of those areas that they've drawn lines around, and that gives them the infarct size for a given heart. It's very inaccurate, as you can see, because of this coastline paradox. And you can use the caveat, we did this at 20x, or we did this at 5x or 10x, and we use this segment length for image J. If you read papers where people do this, they very rarely tell you all that information. So what's a better way to do this? Based on, yeah,
typically, one of the things that is often done, and using this as a sort of an auto border routine, you probably use this, Chris, that you define the threshold. And so you say, okay, I'm going to use a contrast between the red and the white, and I'm going to have to define this much of a threshold. And if it's above, if the difference is above this threshold, I will draw the line there. But if the difference is below that threshold, I'll assume it's contiguous.
That's right. Yeah.
And so the problem here is it's completely subjective. It's not objective, it is subjective, because I can get you any area that I want. In fact, I can make the whole thing look like there's no area there at all by setting the threshold high enough. So it just doesn't, it's not enough to trigger. Or I can get essentially the whole entire heart, I can say, triggers, because I've set the threshold so low that even the hint of a white pixel or a small, any deviation from absolute red will trigger it. So that this now becomes a completely subjective issue, which is the area of, which is why a lot of this is not reproducible.
That's exactly right. And that is the central problem with using this as a method to try and assess a biological structure. So, and my argument is you should not use that method. It is absolutely the wrong method to use, because all of the caveats that Dr. Pierce brings up, and there are things that he didn't bring up, like white balance for your camera and white balance for the monitor that you're using. Can you detect the contrast in a way that is reproducible across different operators? So those are things that you may or may not have talked about already with Monica or Dr. Wilson or Dr. Yellen, but that's a central problem. The tool that you're using then depends upon set conditions that are very difficult to reproduce across different instruments, okay? And on top of that, you got a human being, and there are days, quite frankly, when I'm lazier about my assessment of an infarct area than other days. So it depends on my level of attention, my level of focus, how bright or dim my monitor is when I'm trying to draw those images, the resolution of the pen that I'm using within image J to try and circle those areas. So there's all sorts of bias that we're not controlling for. And the goal is to control for that bias and get rid of that bias. So what would be a better way based on the things we've talked about so far?
Automating versus on certain properties.
Okay, which properties? Let's go back to our fundamental parameters, and you tell me, oh, there's a hint.
If we're doing tissue, we need area, I mean, we need everything, I guess.
Right, so you need
What's
three
your
dimensions.
question?
If we're talking about the volume of an infarct, we need 3 dimensions. So what is the probe that we would normally use?
Dissector.
Well, you could,
Tissue?
that's counting number, but we're talking about volume. We're interested in the volume of the infarct, right?
Oh, well, yeah, I mean, point right there.
Yeah, so the first order thing, we could go to area and look at surface and use line counting, which is another way to do that. But really what we want is volume. So why screw around and do all these other second order parameters? I mean, they're not second, they're first order parameters. But why would we have to complicate the method when we can just use a point that we know the area of and overlay a grid of points on top of that infarct, and then use those points in the area of those points so that we can determine what the actual infarct is. So you can change the resolution of your points and the grid density of your points or your crosses here. But you're going to have a much more accurate estimate than trying to draw a circle around it like this. So what we do is we use cavalieri point counting to actually assess volume in an unbiased way. Now, people who do infarct work, about half of them know that and use it, and about half don't. We can do that in our AIM. So we have the tools already to do that in an unbiased way. Here's another aspect of that problem. So when you've got a 3D object and you're taking 2D sections through it, basically what you're doing is getting little circles and ovoids off of that particular thing that you're sectioning. And then you try and reconstruct that. So that's what we do when we do 3D reconstructions using 2-dimensional planes. So we have to carefully distinguish the structure, the object of interest that we're trying to probe, that's a 3D object, the probe that we're using, so the section plane, the angle of that plane, where it intersects the object, the image window, the grid that we're using in order to try and quantify the area of that object with the plane. And when we're talking about sections, it's the intersection between the structure and the probe. So we know that there is a physical dimensionality to the plane that we're talking about. And the profile is the 2D plane through the object. So that's what we get. So we end up trying to figure out how to quantify this. It's called the corpuscle problem. And this is something that's been around for a very long time. People have known about this since the 1700s. And part of this comes from looking at stratigraphy in geology, where you're trying to figure out how old the Earth is, which is a problem that we deal with contemporarily, even to this day here at Loma Linda. So when you've got a bunch of 3D objects that are embedded in a matrix, and you're trying to take planes through those objects, you have these corpuscles, and you have to figure out which of these objects is attached to which other object. So it's easier when you've got a computer to help 3D reconstruct that particular object and from the slices. But really, we need to deal with the size and orientation problem. You know, how do we know which object is attached to each other as we go through each of these serial sections with these 2D planes? So that's a fundamental problem called the corpuscle problem. And when we think about a bias correction factor, this is something that was published by Wixel and de Hoff-Rhines early on, 1925 for Wixel, and de Hoff-Rhines refined a little bit. The number of objects in a given volume is what N sub V is. That's equal to the number of particles per unit area, N sub A, over the mean particle diameter. So this works great if you're dealing with objects that are relatively spheroidal or ellipsoidal, not things that have high fractal order. So when you're trying to do this, this is a bias method, but they're trying to unbias this as much as possible by using the mean particle diameter to normalize the objects that we're actually counting, number of particles per unit area. So that's the limitation there. I just want to give you an example of a bias method. Okay, what's the unbiased method to do this sort of thing? Well, for counting objects, we can use the optical dissector. So we're talking about volume like we're talking about before, we can use Cavalieri points. Cavalieri points are sort of an iteration before using an optical dissector to do this kind of counting. So what is an optical dissector? This comes from a paper by Gunderson in the Journal of Microscopy back in 1986. And once again, we're talking about this interface between technology helping the optics that we had before. We've had great bright field optics for over 200 years, believe it or not. If you look at a Zeiss scope from the latter part of the 19th century, a newer Zeiss scope is not that much better when you're talking about chromatic aberration and everything else. I know this from personal experience because I have a friend down in the surgery department at UCSD, and he has an 1891 Zeiss scope. And I've looked at neurons and brain sections in that 1891 Zeiss scope, and it looks just as good as my Olympus or Zeiss scope that I have in my lab. 1891. So optical resolution is not the problem when we're talking about counting. How do we do this in a way that's unbiased? That's really the issue that we're talking about. So we're counting objects through a known fraction of a reference space. I'm going to get back to this concept of known space too. The reference space is key. There's a guard volume above and below the dissector. So when you prepare tissue, for those of you who've done this kind of work and done sectioning, you know that the top of the slice and the bottom of the slice, they're all jacked up. They're irregular. The microtome or whatever you're using to slice that particular piece of tissue is going to have pits in it that you can't see because metal, particularly steel objects, have fractal order too. So as you zoom in on a blade that looks perfectly smooth to our eye, and you use a microscope at 40x or 100x, you're going to see this pitting, and that tears up the tissue as it goes through the tissue to make the section. So you have to be careful to have a guard volume where you're not trying to assess something with an unbiased counter above and below the dissector. And then you can count any unique point on that particular object. All right, so this is mostly about counting objects when we're talking about the 3D dissector, the bottom parameter. And here's how this works. So we use an optical dissector. Here are a whole bunch of objects that we're interested in. The red lines are exclusion lines. And notice that they extend beyond the box by about half the box's diameter or length. So if something touches the exclusion line, even if it's within the optical dissector, we do not count it. So this is a way to reduce bias in our counting. If it touches the inclusion lines, which are green here, if you're red-green colorblind, then that could be a problem to see. But trust me, this line that I'm overlaying now with my cursor is a green line. That's our inclusion line. So notice that if something touches the red, we don't count it. If something touches the green, we count it. If it's in the middle of the dissector, not touching any line, we count it. All right, that's the way to get rid of this bias in counting objects. And this is what it looks like as we, unfortunately, I don't have a good animation to do this. This is something we would normally do on the microscope. Here's the top surface where it's a little bit rough. We're going to avoid counting there. As we start to go down through the tissue, and here we're going from -3 microns to -18. So it's basically, we're talking about a typical 20 to 25 micron section that we get with a cryostat or a sliding microtome. So as we move down, notice this particular object touches the exclusion line. And the way to do this is you want to make sure the object is in the best focus that you can get. And then literally you can take your cursor and click on it. In this case, we're not going to count it because it's on the exclusion line. So we go farther down. We see another cell object over here coming up. And we can count that one because that's the best focus that we're going to get on that. As we go farther down, we finally see another one here at the bottom of that particular section, and we count that. So really, we'd only have 2 objects that we counted as valid here in this particular section. And that depends on being able to take this 3D optical dissector and slide it down through the tissue in space. And that's why we need the computer to do that. Okay. So what else do we need to know? So for efficient and unbiased sampling, we need to have a random start. And the way we do that is we overlay, so you guys probably recognize this as an old section of brain. So this is through cerebellum, looks probably like cat, could be rat, but probably cat. And notice we have our optical dissectors here. We can overlay them in a grid, and you can change the relative resolution of that grid, change the distance between the dissectors if you like. And that depends on a bit of mathematics that I'm not going to go to for this particular lecture. But if you're interested in that sort of stuff, I can help you go through the math. But the idea here is that you have to have a random start. Once we've laid down this grid, we can't just go left to right like a boustrophodon, the turning pattern of oxen plowing a field, where you go like this. Instead, what we do is we use the computer and we say, we need to get a certain number of cells, so we need a certain number of dissectors based on the resolution, the area of the dissector, the volume of the dissector, and the size of the cells or objects that we're trying to count. And then we need to start somewhere randomly. And the computer can go here, and then can jump over here, and then can go over here and over here. So that's random sampling within the region of interest that we have, or the reference space that we're looking at. So we don't necessarily want to use the boustrophodon method where we go back and forth in a regular, reliable pattern. That's not what we want. We want to be able to randomly sample within the dissectors that we have. You can do this using this way, but you need to start at a random place if you're going to do it, and change the direction that you assay that tissue. All right. Okay, so we get back to this idea of Cavalieri principle again, using these points in order to determine volume. So when we do that, a big problem that we see is what happens if tissue shrinks, or you have problems with the tissue that suggests there's a pathophysiological change in there. How is it that we can figure out how big a difference it is from healthy tissue to a pathological piece of tissue? Or here's the other consideration. When you're fixing tissue and you're using something like formaldehyde or paraformaldehyde, you're going to get a certain amount of tissue shrinkage in that tissue depending on how old it is. Younger tissue shrinks more than older tissue. Think about that for a minute. I'll show you a slide. So here's how we would use the Cavalieri point count method to assess the volume of tissue that we have. Say, for example, here that we're interested in white matter only. We would only count the area that the Cavalieri crosses represented within white matter. And you can see that there could be some subjectivity to this, as Dr. Pierce mentioned before, because we've got a relatively low resolution Cavalieri point grid here. We know the area because we know the length of the axes, but maybe we could increase the Cavalieri point grid in order to get better resolution at this particular magnification for that tissue. We could do that. However, it's still better than trying to draw a line around the white matter and use that problem of fractal dimension to cripple ourselves in understanding the actual volume that we're trying to quantify, okay? And here it's a matter of the number of points or crosses that we have times the area of each point times the number of times that we have to have the point grid there. So this is a way to calculate the volume using that Cavalieri point counting method. Notice that, you know, here we have an Alzheimer patient post-mortem, and you can see how much shrinkage there is, how much tissue loss there is in those brains. So Cavalieri point counting has been used for that sort of thing. The reference trap. So we're tempted to calculate density, but because of this tissue shrinkage problem, that is not the best way to try and figure out the number of objects that we're looking at in a given volume. So here on the left, we have an older piece of tissue that does not shrink much when you preserve it with formalin. On the right, you have younger tissue, and the interstitial space actually shrinks more because you have other things there. Here on the left, you got more sclerotic tissue. It's even the fatty tissue within an old brain is not going to shrink that much if you stick it into something like paraformaldehyde or formaldehyde. So what you want to do is calculate the total number, not the density, because of this reference trap. The reference space that you're looking at may actually be changed by shrinkage in the tissue. So that's another thing that you have to account for, and the software that we use helps us do that. Okay, for an unbiased design, once again, I just want to refresh our memories. When you're looking at volume, you need to have all 3 dimensions, so you need to use an appropriate probe. For area, you have 2 dimensions, so you need to use a probe that has an additional dimension. Length is 1 dimension, so you need to use a probe that has 2 more dimensions. Number, when you're just counting, you need to use the dissector to actually do the count. Okay, everything has to be 3 or greater. All right, so in the AIM, we have unbiased stereology using the Stereology software, something that comes from a company. There's only 2 companies currently that make unbiased stereology software. One's MicroBright Field, and the other one is the Stereology Resource Center. I've worked very closely with the Stereology Resource Center over the course of the last almost 20 years now. So, but the other piece of software that we have within the AIM that makes it really useful to use Stereology and some of the 3D reconstruction tricks and contrast imaging that we can use is Amaris bitplane. So we can actually use Amaris to give us other structures that we can use with different stains, and use Stereology and Amaris to 3D reconstruct the tissue area of interest that we have, the reference space that we're looking at. So we can use Stereology to count the number of neurons, but if we want to reconstruct the 3D volume of that in a way that can be represented in a really cool way in a paper or on a website, then we can actually use Amaris bitplane to lend structure to the other things that are around the objects that we're counting. So we're combining unbiased stereology with these other imaging techniques that are available to us through bitplane. So that's something we can do in the AIM. Okay, so variation estimation. One of the things that we see, particularly if we're interested in development, is we see a lot of changes in variability. So here we're looking at microglia number on the left-hand side. Notice we're not talking about density here, we're talking about the total number. And then we're looking at age, because we know that microglia sort of turn on and become more active and more prolific as an animal ages. So in this case, we're looking at mice, I think, is where this comes from. At 4 to 6 months, we have a certain amount of biological variation with a median number of microglia. As the animal ages, we see that increase. But notice that the variation increases a bit too. So trying to estimate the variation is also one of the things that the 3D dissector makes more readily available to us through the computer. So biological variation is important. Age-dependent variation in a given species is important as well. So when you're thinking about counting something, the way we used to do it is we literally would take a side tube off of a microscope. We'd look at each section that we were interested in, and we would draw the section and count the number of cells, or we'd use a clicker to count the number of cells as we look through the microscope. So that can be very inefficient because the goal there is to try and count everything of interest. The whole idea behind unbiased stereology is not to take that kind of time. You need a certain number of objects counted or a certain number of capillary points on a given reference space in order to get an accurate, and this is a mathematically validated accurate measurement of the number of objects or the volume or area that you're interested in. So here we're talking, if you have a strong effect size, a large effect size, a moderate effect size, or a mild effect size, here's the power, the number of reference regions that you need to count, and the sampling stringency, that is how regular the number of dissectors need to be. So don't worry too much about the numbers because this varies, depends on the region that you're looking at and the kinds of objects that you're trying to count. But the idea is, how many sections does it take to actually get a real mathematically validated statistical difference in any of the 4 parameters that we talked about before? So if you have a large treatment effect, you need a smaller n, that makes sense. And you can use less sampling stringency. So coefficient of error, coefficient of variation measurements are basically how we determine sampling stringency. If you have a moderate effect, you need a slightly greater power, of course, and you have to use a more medium density grid instead of a low density grid. If you have a mild effect, you've got to count a lot and you have to use a high sampling stringency for your dissector placement or whatever probe that you're using. So that's just the basic relationship. But regardless, if you're using these tools, you don't have to count every object that's on every slide. So the time efficiency is much greater when you're using these unbiased methods. Okay, here's another source of uncertainty. Let me talk about some of the caveats to use of any stereological method, but even unbiased stereology. If you have a lack of a well-bounded reference space, so if you're looking at a brain structure, if you're looking at hippocampus or a gyrus that has very clear delineation of layers or cell types, and you can draw a line around that, within that region, and we're not using that line for anything other than to define where that reference space is. After that, you can put in the cavalieri points or crosses, you can put in the dissectors and start counting the cells that are there or figuring out the area that you're actually looking at. But we're not using the line for anything other than to constrain the search region that the microscope and computer are going to use in order to do the random sampling and do the counts. So within that reference space, then we can distribute all the dissectors that we need to do accurate counting, all right? Accurate and precise. Another source of uncertainty is what kind of staining we have. If we have a poor antibody and we can't get much immunostaining penetration, and you know this happens all the time. Here are the stained region with this bright field antibody. And really we're interested in neurons and we're seeing capillaries here. So how we distinguish the object or the protein that we're interested in or the RNA that we're interested in depends on how much penetration we get and how much staining we actually have. So this is actually a cross section going through a slide. Normally we'd be looking at it this way, going down, but now we're crossing through to see just how much penetration we get with the antibodies that we're looking at for staining. And you can see that we don't have a lot of penetration in this particular section. So you want to optimize your staining for the thickness of the sections that you're trying to quantify something in. And of course, we've talked about the coastline paradox already, the resolution that you're looking at that particular tissue. So there's a balance, a practical balance between high resolution optics in counting and low resolution counting in optics. And as Dr. Pierce mentioned earlier, you have to make that decision. But if you're using unbiased methods, regardless of the resolution, you have to report the resolution that you use, of course, but regardless of the resolution, you're going to have a mathematically valid method of counting those 4 parameters if you're using unbiased sampling methods. So there are 2 companies I mentioned before. There's Micro Brightfield. They make Neurolucida. Some of you may have used Neurolucida for 3D reconstruction of neurons and microglia and astrocytes. They have a tool called Stereo Investigator. That's their unbiased stereology tool. I would encourage you to go to their website and look at it. There's a video here that I give you the link to that is great, sort of tour de force through their software. And that video shows cavalieri point counting. It shows 3-dimensional object probes like spheres. And it shows the optical dissector method, all 3 of those just in a 5-minute video. So that company is huge and their stuff is very expensive. This tool is about $20,000 for the full Micro Brightfield setup. And I'll show you some of the equipment that you need for this sort of thing. The SRC, the Stereology Resource Center, is the company that I've been working with for a long time. And it was started by the guy who wrote most of the books that we have on unbiased stereology. His name's Peter Mouton. And I'll show you those books in a minute. But they have Stereologer is the name of their software. And they have been funded by NIH and NSF to do some advanced development and neural network learning embedded in Stereology. So their goal lately has been to automate stereology. So you have to teach the Stereology software how to do the initial counting, but then after that, all you need to do is load up slides and it will do the counting itself. And it works pretty well for some things. It's still in beta. We actually have a beta version of the software in the AIM right now that we're testing. And here's a link so that you can look at not the automated version of Stereology, but the regular version of Stereology. And you can see basically the same thing between Stereo Investigator and Stereology. It uses the same things that we're talking about for determining the 4 probes. So this is basically what you need for an unbiased stereological setup. You need a good camera. You need a motorized stage, a very precise motorized stage, because you need to accurately determine where you are in Z space, X space, and Y space as you're moving through that reference region and trying to count the objects or determine area or volume that you're interested in. And you need a pretty good microscope to do that, of course, but most microscopes these days can do this quite readily. And then you need a computer that allows you to look at the areas of interest and do the counting when you're doing it interactively. So the world's first computerized stereology system was from SRC, the Stereology in 1996. Since then, Micro Brightfield has developed their own. Here are some of the things that you can see. So you can do the outline of the reference region. You have the optical dissector. You can measure volume, area, length, number, and variation. The computer helps you do that, and it depends upon having accurate motors to do the focusing and a good stable XY stage and a good video camera to do this counting. So basically what you're using is a mouse to click on the objects or distribute cavalieri point counts. If you're just looking at volume, then it'll go ahead and put the cavalieri point counts on there, and as long as you define the reference region, it will give you the volume as you go through the entire sample. So you don't have to worry about the image J nonsense and the interoperator variability. And we've tested this to make sure that we have very low interoperator variability for the folks that have been in my lab. So now, as I mentioned before, the SRC is developing this automated stereology system, and they're really, right now, it works really well for microglia that are IBA1 stained. So if you have a bunch of tissue that you've got microglia in, you're interested in defining the volume area and doing some counting for those, then the automated stereology system works pretty well. It requires very little training because most of the IBA staining that we see is pretty high contrast, like these two images. And it will go through and take the sections that you feed it and go through and actually do that counting for you. So you don't even have to go through and do the click on the object within the dissector once you train the automated stereology system. Okay, and they came out with that in 2017. As I said, we're one of the beta sites. So right now, we've done a little bit of work with it. This is automated counting. They've done some comparison work. Notice that the green are objects that have been accepted because they're either within the dissector and not touching an exclusion line, or they're touching an inclusion line. And notice that we exclude those guys that are in red. Usually we use 10 to 20x in order to do this. It's much higher throughput than manual counting. It's about 10 times faster in our experience with some of the tissue that we've used. So here's a comparison of manual versus automatic versus control and TG4510 mice, which are an AD model, Alzheimer's disease model mouse. And you can see that the percent difference is only 2% between manual and automatic for each of these categories versus across the groups. Okay, so it's pretty good. It's not bad at all. It still needs training. Here are the 3 books that I recommend if you're interested in this. This Principles and Practices of Unbiased Stereology talks a lot about the fundamental theoretical aspects of unbiased stereology. There's an even shorter version called Unbiased Stereology that came out in 2011. And then the newest edition of Dr. Mouton's work is Neurostereology, where he's focused strictly on counting things that are within the CNS or the peripheral nervous system. So that's what this book is about. And it recapitulates a lot of the information that's in these other 2 books. If you're really just interested in getting a rough overview, then the middle book is the best. But if you want more of the theoretical background, some of the things I've talked about today are just alluded to, then you can look at the Principles and Practices book. And I have that. I have a copy in the lab, and I have a copy in my office if you want to borrow it from me. This book is very nice, the Neurostereology book, if you're interested in counting neural structures. Okay, there are a couple places that he's working with. So the SRC is down in Clearwater, Florida. So he's working with some colleagues down at University of South Florida in the BIRD, Alzheimer Dementia Center and Neuroscience Institute, and the Department of Computer Sciences and Engineering. This guy, Dmitry Goldgoff, is the guy who does most of the neural network coding for the automated version of Stereology. So if you're interested in talking to those people, I can certainly put you in touch. So just by way of summary here, unbiased or design-based stereology eliminates the variability, as much variability as we can. It doesn't eliminate the biological variability, but it lets us quantify the biological variability and the bias found in traditional Euclidean-based stereological measurements. Unbiased stereology provides a mathematically accurate and precise foundation for obtaining the 4 first-order parameters: volume, area, length, and number. The development of these computerized unbiased methods starting in 1996 makes it much easier and more efficient to try and quantify these 4 parameters when you're looking at your tissue. We have new technology that now melds 3D reconstruction and unbiased stereology in order to develop the best practices. We have that in the AIM, and that includes unbiased stereology and MRS and bitplane software. And we've been beta testing this new automated unbiased stereology, which even makes this faster. So rather than counting 1,000 cells and then going to 200 cells when you're doing the unbiased stereologies to still get an accurate representation of the tissue, now you can use the unbiased stereology and you don't even have to count the 200 cells yourself. You maybe count 10 cells and then turn the automated unbiased stereology system loose on it, and it'll count for you. It's like having a dedicated robot minion. That's about it. So the people who've worked on this here at Loma Linda are Rhea Johnson, my former tech, who's now in medical school, and Monica, who's on our call right now. And then the people I've worked with pretty closely over the last 15 to 20 years of my career, Peter Mouton and Scott McElhaney at the Stereology Resource Center. Okay. It's a lot of material, I know. Questions? Does it make sense?
Sure.
Was I completely obscure, or did you get what I was trying to say?
Oh, we got it.
You got it. Did I beat it to death? That horse is dead. You don't want to hear about unbiased stereology anymore?
No, I actually feel like it's really interesting.
Oh, good. Well, that's good to hear, Kayla. How about you, Fuller? Was this useful for you with your organoids?
Yeah, it was definitely useful. I'm trying to look at all the different methods and techniques so I can do the 3D imaging.
Hmm.
So
Well,
really
I would
trying to figure out
recommend,
to do
if
it.
you want to count things in your organoids, then use Stereology, but then do the 3D reconstruction with your markers using Amaris.
Mm-hmm.
Bit plane's really nice for that. It looks really good.
Yeah, I tuned into their video session yesterday.
Oh, cool. Okay,
Yeah,
great.
they do some cool stuff.
Hmm. Yeah, I only had that one slide on Amaris because I think somebody else is going to cover that. But
Yeah, so the Imerus is having a full series of webinars over the next month, and so I've kind of put those on the schedule for them, and then we're working on getting VPN access for everybody so that they can work directly on the box.
oh, awesome. That's cool. Yeah,
And then
because Sean's got a really high-powered computer in the AIM that can do a lot of this work with the bit plane stuff.
yeah, I put up the videos that you were linking to there. I put those up on our Canvas site, and then I also linked off to one that shows different cameras and the camera solutions.
Oh, cool.
Because we haven't really covered the hardware in that way. We've talked more about just kind of fluorescent molecules and the generalities of using a confocal microscope, but not going into a deep dive into the technologies.
Sure. Yeah. I probably talked too much about CCDs and CMOS chips, but anyway.
No, you have to have a good global overview, because what this really is this is the first page in a book of stereology, and you have to then develop your own chapter to apply these methods to your problem.
Absolutely. Yeah, that's a good way to put it.
Right. So, I mean, I'm very interested in trying to raise the level. I've tried to use the Calvary principle before, but a lot of times I'm trying to avoid the use of the counting of objects and averaging, summing the area under the intensity number curve.
Mm-hmm. Yeah, that makes sense. I mean, you can do that sort of thing, but the cavillary points work really well with the computer. It's easy to do.
Yep. It saves a lot of time.
Mm-hmm.
Because all this, everything that I did in the old days, Chris, was all done manually.
Well, the first time I read that book, that beige book that was on the left, and then I started making my own transparencies with dissectors on it, and literally taking the sections, using my side tube, and putting the dissectors on and counting that way on a pad of paper. So, because I couldn't afford the computer when I first started in my assistant professorship. So, once I got the optics and the computer, things were much faster. But still, it was more efficient than trying to count everything just using an optical tube.
Right. But I remember many hours spent with an inclusion and an exclusion line and counting, cells and whatnot. But there's so many variables, because anytime you're using a stain, for example, if you're doing IBA1, the conditions of the stain are so critical, because if you have a little bit of deterioration or you have a bad prep, you won't know if it's because your tissue is not, really showing activated microglia, or because you had a bad stain. So
absolutely,
are still the fundamental principle of a good control prep is really essential for getting even good stereology results, I think.
No doubt. And that's why, those uncertainty slides that I put up, where if you got a bad stain, or you don't have good penetration in your stain, or you're using the wrong resolution for the tissue that you're trying to record from, you're going to have some serious problems. Absolutely. And this is not the panacea for those problems. You got to sort out the staining before you can really use the unbiased stereology effectively.
Right. So one of the things that has really been helpful for us is we use a standard section, and you will choose a standard section at the beginning of a project, and that several of those standard sections will be in every single staining run, so that we use that, and then we normalize relative to that standard. That's our standard reference, and that really helps eliminate user error and variation in antibodies and all those other kinds of things. So good controls are essential, but once you have the good controls, then the stereology it looks to me like it's going to save a lot of time.
It does. And it just takes a little while to get used to the software, but once you do that and you got somebody who's cranking through it, you can go through a lot of tissue pretty quickly.
Now, can you use machine learning to help even shorten the time further?
So the automated version, which is based on neural network, it's got a neural network learning algorithm. It's literally 10 times faster than the humans in the validation work that they've done, because I've helped them with an NSF grant for this. So they have some support to continue developing the automated stereology method. But it's 10 times faster, and it could be faster than that. That's not on the fastest hardware. So if you've got faster hardware and a good stage, then it could be 100 times faster, probably.
So where this becomes really potentially very, very important is where you have a consolidated infarct in an adult brain due to a clot or an aneurysm rupture, et cetera. It's a little bit easier. You still always have the fractal problem, but you can define a resolution and get a number.
Yeah.
Where it's really tough is in immature brain, where you don't have a consolidated infarct, but you have a whole range of micro infarcts, and you probably have 20 or 30, and trying to go through each one of those is really time consuming and very, very difficult. And it's also a very, very different pattern of morbidity.
Oh yeah. Yeah. It's best to use an automated system for that then. Yeah.
Yeah.
No doubt about that.
All right.
Other
Any other
questions?
questions?
No.
Okay. Thank you for your attention. If you have any other questions, just let me know. I'm perfectly happy to help you with this stuff. Monica is very well trained in all of the software too, so she knows how to use it and is a big help for getting people up and running.
Thank you, Dr.
All right.
Mason.
You're welcome. Thanks for your time. Bye, guys.
Thank you very much.
Bye.
Mhm.
Thank you.
All right. And we will call it a day.